Right now, as you're watching this, time is moving slower for me than it is for you. I'm not joking, and by the end of this video, you won't even be sure time exists the way you think it does. Stick around. Welcome back to Science and Beyond. Today, we're going to break time itself. Let's go. What is time? Imagine you wake up tomorrow, but the sun never rises. Your clock stops. Nobody grows older. Nothing changes, anywhere. Would time still exist? Scientists actually define time as the measurement of change. Without change, there's no way to know whether 1 second has passed, or a million years. In other words, time isn't some magical ticking force in the background of the universe. Time is just how the universe keeps track of events happening. So if time is really just change being measured, here's the terrifying part. What if that measurement doesn't run at the same speed for everyone? The equation that broke physics. In the early 1900s, one man, Albert Einstein, said something that made other scientists think he'd lost it. He said speed itself can slow down how fast change happens for you. Not metaphorically, literally, and he proved it with this. T prime equals t over the square root of 1 minus v squared over c squared. Don't worry, this isn't as scary as it looks. T prime is time for someone moving fast, like an astronaut. T is time for someone standing still, like you. V is their speed. C is the speed of light. Now watch what happens as v gets closer to c. The bottom of that equation shrinks, and t prime grows. Which means, the faster you move, the slower change happens for you, the slower time passes. Sounds insane, right? Except it's been tested, repeatedly, and confirmed. But here's where it gets weird. This exact equation is running inside a device you're holding, probably right now. Your phone is hiding this. GPS satellites fly around Earth at insane speeds. Because of that equation you just saw, their onboard clocks tick slightly slower than clocks down here. But wait, it's not that simple. There's a second force fighting against the first one. This second equation comes from gravity, not speed. T prime equals t times the square root of 1 minus 2 gm over rc squared. G is gravity's constant, m is Earth's mass, r is how far you are from Earth's center. Satellites are farther from Earth's center than you are, so gravity is weaker up there, which makes their clocks run faster. So you've got speed pulling their clocks slower, and gravity pushing them faster, at the exact same time. When engineers do the math on both, satellites end up gaining about 38 microseconds every single day. And if nobody corrected for that, your GPS would drift off by miles within 24 hours. You'd be told to turn onto a road that doesn't exist. And that same gravity equation? It's happening inside your own house, right now. Proof. Your roof is aging faster than your floor. Look back at that gravity equation. The closer you are to the ground, the smaller r gets, and the slower time moves. That means your ground floor is very slightly younger, right now, than your roof. Scientists proved this with ultra-precise atomic clocks. You'll never notice it in your lifetime, but the math says it's real, and it's happening under your own roof, at this exact second. Now, if a house can do that, imagine what a spaceship could do to an actual person. One twin comes back younger. Picture two twins. One stays on Earth. The other flies through space at insane speed for a year, then comes home. Using that very first equation, the speed one, we can calculate exactly how much younger the traveling twin will be. And this isn't a thought experiment anymore. Astronauts on the International Space Station really do come home microseconds younger than the version of them that stayed on Earth. Same equation, same math, confirmed. So if speed alone can do that, what happens when gravity gets turned up to the most extreme setting possible in the entire universe? The point where time stops. Take that gravity equation from before, and push m, the mass, to the level of a black hole. As you get closer, r shrinks and shrinks, until you hit one very specific distance. R sub s equals 2 gm over c squared. This is called the Schwarzschild radius, the exact edge of a black hole. Right at this point, plug it back into the gravity equation, and something wild happens. Time dilation becomes infinite, from an outside point of view. In plain English, if you watched a friend fall toward a black hole from a safe distance, you would never actually see them cross that edge. Ever. they'd appear to move slower, and slower, and slower, fading, frozen, forever. But from their own point of view, they'd fall in completely normally, feeling nothing unusual at all. 3 equations, 1 universe. So let's connect everything, back to that very first question, what is time? We said time is just the universe measuring change. Equation 1 showed us speed can slow that measurement down. Equation 2 showed us gravity can slow it down too. And equation 3 showed us that near a black hole, that measurement can stop completely, from the outside. And every single day, without you ever noticing, satellites above your head are running the first 2 of these equations simultaneously, correcting a 38 microsecond gap, just so your map app can tell you where the nearest coffee shop is. You're not just checking your phone. You're using 3 of the strangest, most mind-bending equations ever discovered, completely for granted, dozens of times a day. Okay, be honest. Which part actually broke your brain? The idea that time is just measured change? The speed equation? Or the black hole? Comment below. I read every single one. If you'll never look at a clock the same way again, hit subscribe, because we do this every week here on Science and Beyond. See you in the next video.